We're going to continue our study today on ratios and proportions by talking about indirect measurement. Now, indirect measurement, as the name suggests, is a way for us to be able to measure something that would be otherwise impossible, maybe because our measuring tools are not long enough or because we physically cannot reach certain heights. It allows us to use ratios and proportions in order to measure something. So indirect measurement allows you to use properties of similar polygons to find distances or lengths that are difficult to measure directly. So for example, let's say you're trying to measure the height of this pyramid. Now it might be very difficult to actually measure this height if you are unable to actually reach that without a ladder, without other tools. But you're able to come up with the measurement here because you might be able to measure the shadow. So we're going to suppose here that there's this guy here, Thales. He's a well-known mathematician from a long time ago. And you can relate Thales' shadow with the pyramid's shadow, and those are definitely things you can measure or have someone else measure. And because you can measure Thales' height, you can determine the pyramid's height by using this proportion. Let's take a look at an example together. A fire hydrant 2.5 feet high casts a 5-foot shadow. How tall is a streetlight that casts a 26-foot shadow at the same time? Let h represent the height of the streetlight. So here's a picture. So there's a fire hydrant that's 2.5 feet tall with a 5-foot shadow. And then there's the streetlight that casts a 26-foot shadow, and you're trying to determine the height. So what we're going to do is I'm going to make one side the shadow and one side the height. So on the left, I have the hydrant's shadow in the numerator, and then the streetlight's shadow in the denominator. So that's 5 feet and 26 feet. Now on the right-hand side of this proportion, I'm going to have the height. I'm going to keep this consistent and have the hydrant's proportions in the numerator. So the hydrant's shadow is in the numerator, so the hydrant's height will also be in the numerator. And that was given to us as 2.5 feet. The streetlight's height will go in the denominator, and because that's what we're trying to solve for, and it told us to let h represent the height of the streetlight, we're going to put h in the denominator. Now we can cross multiply. So we have 5 times h equals 2.5 times 26. And then we multiply, we get 5 times h equals 65, divide both sides by 5, and we get h equals 13. So the streetlight is 13 feet tall. Let's look at example 2. A telephone pole casts a 24-foot shadow. Belinda, who is 5 feet 8 inches tall, casts a 7-foot shadow. Find the height of the telephone pole. Alright, so here's our picture. There's Belinda, who's 5 feet 8 inches, and her shadow is 7 feet. And then we have the telephone pole. We don't know how tall that is, but we do know that it has a 24-foot shadow. Now notice here we have things in a number of different units. You can either change everything into feet or everything into inches. If you don't want to work with decimals, then I would suggest changing everything into inches. So since there are 12 inches in a foot, the 24-foot shadow is going to be 288 inches. The 7-foot shadow is going to be 84 inches. And then Belinda, who is 5 feet 8 inches tall, we just have to change 5 feet into inches and add that to 8, so that gives us 68 inches. Okay, so now let's go ahead and write our proportion. Let's keep the shadow on the left and then the height on the right. So let's start with Belinda's shadow. So that would be 84 inches. And then we'll put the telephone pole's shadow in the denominator, so that's 288 inches. And then on the right, we're going to work with the height. So the height of Belinda is 68 inches. And then the height of the telephone pole goes in the denominator. We need to solve for that. Alright, so cross multiplying, we have 84 times h equals 68 times 288, which is 19,584. Divide both sides by 84, and we get h is 233.14 inches. And if you want to change that back into feet, you get that this is about 19.4 feet. So that is the height of the telephone pole. Let's look at another example. On a set of blueprints for a new home, the contractor has established a scale that states that half an inch is equal to 10 feet. If the buyer would like a kitchen to be 18 feet in length, how long should the kitchen be in the blueprints? So we're going to go ahead and use this scale for our proportion. Now we're told that half an inch is equivalent to 10 feet. We're trying to determine if a kitchen is 18 feet in length, how long the kitchen should be in the blueprints. So notice here I'm putting the blueprint in the numerator, and I'm putting the actual measurement in the denominator. So that's going to be 0.5 inches over 10 feet, which is equal to x number of inches over 18 feet. Now you can feel free to change everything into inches or everything into feet. But in this case, as long as we solve this and remember that the numerator is in inches, that should be fine. So cross multiplying, we have 10 times x is equal to 0.5 times 18, which is 9. And divide both sides by 10, and we get x is equal to 0.9 inches. So in each of these examples, we were able to solve using a proportion for some measurement that was perhaps more difficult to measure out, whether it's the tools that you don't have to measure, or perhaps it is a height that you cannot reach, but we were able to determine what those measurements were without actually directly measuring it, because we're able to use similar figures to write a proportion and then to solve that proportion.